What specific problem does the Kimi k1.5 algorithm aim to solve in the context of multimodal language models?
The Kimi k1.5 algorithm aims to address the limitations of traditional language model pretraining, particularly the constraints imposed by static datasets and the need for high-quality training data. By employing reinforcement learning (RL), Kimi k1.5 enables the model to explore and learn from dynamic interactions rather than relying solely on pre-existing data. This approach allows for the scaling of context length to 128K, enhancing the model's reasoning capabilities through improved policy optimization and the generation of coherent reasoning paths. Additionally, Kimi k1.5 is designed to jointly reason over text and vision data, thereby improving its performance across various modalities and benchmarks. Ultimately, the algorithm seeks to enhance the model's ability to perform complex reasoning tasks while maintaining efficiency and adaptability in real-world applications.
Can you illustrate step-by-step how the Kimi k1.5 algorithm works, particularly focusing on the reinforcement learning aspect and the long-caught methods?
The Kimi k1.5 algorithm operates through a structured process that integrates reinforcement learning (RL) and long chain of thought (long-caught methods). Initially, the model undergoes pre-training and vanilla supervised fine-tuning (SFT) before transitioning to long-caught (SFT), where it is primed with a high-quality dataset that encapsulates key cognitive processes like planning and reflection. Following this, the RL phase begins, where a well-curated prompt set is essential for effective training. This set is designed to ensure diverse coverage, balanced difficulty, and accurate evaluability, which mitigates issues like reward hacking. During RL training, the model generates a sequence of reasoning steps, caught, and final answers, with a reward model evaluating the correctness of these outputs based on ground truth answers. The optimization process employs a variant of online policy mirror descent, allowing the model to explore various reasoning paths and learn from both successful and erroneous attempts, ultimately enhancing its problem-solving capabilities through iterative feedback and exploration.
Could you provide a simple, illustrative example that demonstrates the inner workings of the Kimi k1.5 algorithm, highlighting its use of long context and reinforcement learning?
The Kimi k1.5 algorithm utilizes long context and reinforcement learning (RL) to enhance its reasoning capabilities. For instance, when tasked with solving a complex math problem, the model first generates a sequence of intermediate reasoning steps, known as chain of thought (COT), which are sampled autoregressively. As it explores various reasoning paths, the model leverages a long context window of up to 128K tokens, allowing it to maintain a comprehensive view of previous thoughts and decisions. During this process, the model receives feedback through a reward model that evaluates the correctness of its final answer based on the ground truth. If the model generates a correct answer after exploring multiple reasoning paths, it is rewarded, reinforcing the effective strategies it employed, while also learning from any incorrect paths taken, thus improving its problem-solving skills over time.
What are the theoretical or practical advantages of employing Kimi k1.5 over previous methods in multimodal reasoning tasks?
The Kimi k1.5 model offers several theoretical and practical advantages over previous methods in multimodal reasoning tasks. Firstly, it utilizes reinforcement learning (RL) combined with long context scaling, allowing the model to explore diverse reasoning paths and learn from a broader range of experiences, which enhances its problem-solving capabilities. Secondly, the model's joint training on text and vision data enables it to reason effectively across modalities, achieving state-of-the-art performance on benchmarks such as AMY and Math 500. Additionally, the implementation of a well-curated RL prompt set ensures diverse coverage and balanced difficulty, which mitigates overfitting and promotes robust reasoning. Finally, the model's ability to generate long chain of thought (COT) reasoning paths leads to improved coherence and detail in responses, significantly enhancing its performance in complex reasoning tasks compared to existing models.
How was the Kimi k1.5 method validated or tested? Please detail the experimental design, benchmarks used, and the performance metrics that showcase its effectiveness.
The Kimi k1.5 method was validated through comprehensive evaluations across various benchmarks tailored for different modalities, including text, reasoning, and vision. Specifically, the evaluation setup included text benchmarks like MMLU and C-eval, reasoning benchmarks such as Human-eval Mul and Math 500, and vision benchmarks like MMMU and MathVista. The performance metrics showcase the model's effectiveness by demonstrating state-of-the-art results across these benchmarks, particularly highlighting its enhanced long-term reasoning capabilities achieved through long-caught supervised fine-tuning and vision text joint reinforcement learning. Additionally, the model's performance was assessed in terms of its ability to reason, comprehend, and synthesize information over extended contexts, with notable improvements observed in both accuracy and response length as training progressed. This rigorous experimental design and diverse benchmarking effectively illustrated the Kimi k1.5 model's advancements in multimodal AI capabilities.
What limitations or potential drawbacks does the Kimi k1.5 algorithm have, particularly in practical applications or its generalizability across different tasks?
The Kimi k1.5 algorithm, while innovative, has several limitations that may affect its practical applications and generalizability. Firstly, the reliance on a well-constructed RL prompt set is critical. If the prompts lack diversity or balanced difficulty, the model's adaptability across various domains could be compromised. Additionally, the model's tendency to overthink, leading to excessively lengthy reasoning processes, can hinder efficiency during both training and inference, as noted in the introduction of a length penalty to mitigate this issue. Furthermore, the algorithm's performance is heavily dependent on the quality of the reward models, particularly in nuanced tasks like mathematics, where variations in correct answers can complicate evaluation. Lastly, while the model shows strong performance on specific benchmarks, its ability to generalize to unseen problems remains uncertain, as indicated by the focus on optimizing for training problems, rather than ensuring robust problem-solving strategies for diverse test scenarios.